In this video, we'll look at the CNS, and we're going to focus in on the homeostatic mechanisms and its involvement. So let's start off by reminding ourselves what homeostasis is. I'm sure most people have a pretty good idea, but it's all about maintaining that stable internal environment despite changing external conditions. And of course, when we're talking about homeostasis, it's about controlling blood gas levels. So really looking at the level of oxygen, CO2, hydrogen ion concentrations, aka pH of the blood, biological rhythms, body temperature, blood pressure, electrolytes, your fluid balance. So it's a whole lot of things. It's really makes up most of our internal physiology. Goes towards maintaining those homeostatic values. Now, just as a reminder, two big systems that are involved, and we've touched on this before, are the nervous system and the endocrine system. And they both have a role in maintaining homeostasis. And they do work together, but each has its own approach to homeostasis and regulation. So when we're looking at the endocrine system, it's about secreting hormones. So it's about using chemicals into the blood, right? That's the definition of a hormone. So chemical messengers are put into the blood, they circulate around, and they interact with some type of receptor that can read those messages, right? And then act appropriately. So it regulates the function of other cells and can do it from a distance because the blood circulates everywhere. The nervous system sends action potentials to either excite or inhibit target cells. And as mentioned in previous videos and discussions, the endocrine system is pretty typically slow to start, and we're looking at hours or days to have an effect, whereas the nervous system is fairly fast. It's almost immediate in terms of its action. Now, in general, the endocrine system, its effects do tend to last longer than the effects of the nervous system. So let's start to look at the CNS, and really, what are some of the main components in the CNS that are really driving and maintaining homeostasis? Well, two of them are the reticular formation and the hypothalamus. So let's have a look. So the reticular formation, it controls many functions of the internal organs as well as aspects of behavior. And remember, the reticular formation is that it's not one site for it. It's many nuclei scattered throughout the pons, the medulla, and the midbrain that work to do a number of functions. The hypothalamus also has a big role in homeostasis because of its association with the pituitary gland. The hypothalamus makes a lot of inhibiting and releasing hormones that it secretes and moves down to the pituitary, which then regulates the release of pituitary hormones, which then go off and interact with a number of body tissues and body systems. So the hypothalamus really is about interacting with the pituitary. Now, the reticular formation and hypothalamus have many interconnections and allow them to basically coordinate a lot of these homeostatic values. Now, maintenance of these vital functions like heart rate, the force with which the heart pumps, blood pressure, digestion, are largely controlled by the ANS, the autonomic nervous system, and regulates the body's viscera. Now, although the ANS is a component of the PNS, it is controlled by components of the CNS, mainly the hypothalamus. Now, the hypothalamus, not surprisingly, has to receive a lot of sensory input, and especially from the viscera. It receives input from things like the limbic system and the cerebral cortex, because, as I said, the hypothalamus has so much control over the actions of the pituitary, and the pituitary is one of the major endocrine glands in the body. Not surprisingly, the hypothalamus will have to gather up as much information as it can to make the appropriate decisions. And this allows the hypothalamus to basically respond to both normal physiological changes and larger changes. So it could be emotional challenges, and it allows it to adjust its output to maintain homeostasis. Now, just to give you some examples, it really, the hypothalamus maintains homeostasis because of the input that it gets. And largely, it's relaying instructions to nuclei in things like the reticular formation, the medulla. So there's a lot of back and forth. So the hypothalamus is not only just talking to the pituitary, but it's also talking to other centers in the brainstem. So such as, neurons in the vasopressor center. And when stimulated by the hypothalamus, this increases the rate and force of the cardiac contractions and causes the blood vessels to narrow. So we get an increase in blood pressure because all of these things will drive blood pressure up. We also have, now surprisingly, let me back up, if we have the vasopressor center, which increases blood pressure. We have the vasodepressor center, because if you're going to increase it, you have to have a way to also decrease it based on the homeostatic needs at that time. And this is the vasodepressor center, and it decreases the rate and force of heart contractions and opens the blood vessels up. So that decreases blood pressure. Now, there's a whole bunch of other centers too that if we had a lot of time we'd go into that are involved with digestion and control of urination, and there's many, many more. Now, let's take the case of respiration, because it certainly is one of the most important things that we do. And interesting, respiration is one of the few vital functions not under autonomic nervous system control. So the rate and depth of breathing are regulated by a group of neurons in the anterior medullary part of the reticular formation. Okay. Now, this is important because when there's damage to the brainstem, because these are the centers that control your breathing, there's no backup system. Unlike the heart, which has a built-in pacemaker that can cause depolarization of the myocardium, the lungs do not have that within them. So all the control of the lungs comes from this higher center. And there's several factors that influence the firing of these. Now, we're going to come back and talk about this when we talk about the lungs. This is just a quick introduction. When we talk about the lungs, we'll really start looking at the different neurons and how they adjust the firing rate in this part of the brain. And not surprisingly, think about what causes a change in your respiratory pattern: faster, slower, shallower, deeper. It could be something as simple as you start running to catch a bus, or it could be an emotional shock. So, not surprisingly, we get input from things like the cerebral cortex, the limbic system, the hypothalamus, and a number of sensory receptors and nuclei in the pons also have a role. So there's a lot of control centers here. And if we look at body temperature, the hypothalamus regulates body temperature, and it acts as a thermostat, and it tries to keep us around a set point, somewhere around 37 degrees C or 98.6 Fahrenheit. And input is received from these temperature-sensitive neurons located in several areas, the skin, deeper parts of the body, and from neurons in the hypothalamus itself. Now, the hypothalamus, as I said, can have a role in regulating body temperature. So when body temperature increases above a set point, a negative feedback loop is initiated where certain hypothalamic nuclei induce changes to cool the body. And when body temperature decreases, a different feedback loop is initiated that conserves heat. Now, of course, both of these are built on that core concept of feedback loops. Now, fever is an interesting thing, and we'll talk a bit more about it when we get to the immune system. But fever is a temporary resetting of the body temperature at a higher level. And this is really initiated by the hypothalamus. And we'll talk about the reasons and the mechanisms when we get to the immune system. Now, the elevated body temperature often occurs when there's a lot of infectious and non-infectious conditions, and we'll just introduce a few concepts here. There are these chemicals called pyrogens, pyro for fire, heat. Okay, they're caused by pyrogen. They're chemicals secreted by cells of the immune system. So it's interesting. It's chemicals from your some of your immune cells that actually stimulate the fever in many cases. Also by certain bacteria. And these chemicals cross the blood-brain barrier and they interact with the nuclei of the hypothalamus, which has a big role in controlling temperatures. And pyrogens increase the hypothalamic set point to a higher level. And a feedback loop triggers shivering, muscle aches due to the increase in muscle tone and constricts blood vessels serving the skin. And all this is about, especially say if you have bacterial infection, viral infection, this is about increasing the body temperature a bit. Not too much, but if you increase it a bit, you tend to put a stress on the reproduction of the viruses and the bacteria and hopefully slow them down enough that your immune system can catch up and start to deal with them. But of course, if the fever goes too high, then you may risk denaturing vital proteins within your cells, and that gets you into a world of trouble. So treatment's not always necessary for fever. It's more important to address the underlying cause. There's antipyretics. These are things that are used to reduce fever, so like acetaminophen and aspirin, and they block the formation of pyrogens and it allows the hypothalamus to return back to its normal set point.